So the links are starting to go up for the Black History event. It'll be a page that'll be dedicated to you guys. So you should be able to find it in the modules once it's complete. And it'll give you the information about the event. And it'll also give you where you're going to be submitting your document. I remember a couple of you guys were in my 2A class and you guys had to do a video. It'd be kind of nice to see some of those videos surface back up or something along those lines dealing with chemistry for this event for those extra credit points. I told you how much they were worth. Did we talk about the extra credit? Selena?
Yeah, it was 10 for submission and 3 for showing up, right?
That's right, for this event. And then
so it's 13 total then, right?
No. It's
Dang
like that's a nice try though. Oh, actually, I understand what you're saying, right? Because you can actually submit, you can have a submission, and you can actually show up for the event as well too, right? Mm-hmm. But I figure you're going to show up to find out whether or not you won. So. And then the other event, you guys will get 5 extra credit points for showing up to that event. So, you know, hey, I may think about it. I may be able to be swayed because that's a very valid point there, you know, Cassie. Good job.
Thank you.
Good negotiating skills there. So I'll give it some thought.
I was told I should have been a lawyer in the past.
You know, again, I'd like to see some type of representation from chemistry, you know, if possible, definitely in the performance. I'm expecting something incredible from Cassie there now, since she's asking for 13 points.
Well, I have an idea, but it's not chemistry related. It's more like crazy life related.
Oh, that's even better.
Okay, cool. I'm
because
on it.
I think we can all relate to crazy life. Not everybody can relate to chemistry. Now, what was that? Abby, I believe?
Yes.
Yeah.
I am back with my questions.
Excellent.
Wait, so we're doing like a video?
So, yes, you're doing a video.
No.
Abby, it's extra credit, girl.
Abby. Okay, I'll do it.
Yeah. So it's 10 points extra credit towards your test scores.
Okay. Ooh, okay. I'm definitely doing it.
Yep.
I am definitely doing it.
I play guitar, but I'm pretty bad at it.
Hey, but you know, you often will rise to the occasion in front of an audience.
Ayla, you're gonna sound like an angel.
I'll think about it. Oh, I have a question about the where we do our homework for chemistry. Do you have the link for that?
Yes, it should be here. Is it not showing up for you guys?
It just showed up. Chem 101 homework assignment.
Yep.
What about the link for the this speaker event? Is it going to show up as well, or?
Yeah, it's going to show up. It'll be under. We'll have a little. We'll say like events. There's a couple of things that I'm going to start putting in there. Like for instance, Mesa is actually offering you guys to check out the modeling kits. You guys are going to be doing a little bit of OChem. It's going to be very important later on towards the end of the semester to kind of have that modeling kit. Okay.
Okay.
And so they have enough kits. I believe they have enough kits for the whole class to check out, especially since now we're at 11. We're working on 12, you know, trying to break a couple of people down. So I don't want to listen to me.
We only have 12 people?
Huh?
I thought we had 20.
We had 20 initially, but something happened. And then we ended up with 12. So we lost a few of them at NDC. For some reason, I guess it wasn't explained to them that they could have. I'm still going to have the lab session with enough of them. I'm going to have the lab session at NDC as well as Kalinga. And so I think there was some miscommunication. So they didn't re-register. So we had 6 that were there. And then other 6, only one of them re-registered here. So, so I'll be reaching out to them to try to make sure that they understand what's going on.
So lab sessions will be like last semester, like some online and some on campus?
That's right.
Okay.
Most of them will be online. This semester, there's really like 3 labs that you guys can't do online. One of them deals a little bit with radioactivity, and so we need to be confined to certain spaces and certain.
Are we gonna do any balloon
Engineering.
and baking soda popping? Because that's not gonna work anymore.
Well, what do you mean?
It popped in my face.
You know, sometimes that's great for your skin. You know, it helps, get some of the oils out. And
Definitely.
oh, I have to find that video again. Oh my gosh.
It's probably in there. It's somewhere in
Yeah,
there.
I have the recording. I do have the
Yeah.
recording somewhere. I just have to go through them all. So
I remember looking up and seeing Abby, and she was just like frozen.
I was shocked a little.
Yeah.
yeah. Okay, so give me time. The modules page will be it'll start getting caught up. We have some of the lectures and things there already, although I don't have 6 up. So I'll make some adjustments to get the chapter 6 up there for you guys so that you'll have it available. And then I'll also start putting my my lecture notes online. I'll try to do that tonight, get that so you guys will have a copy of the lecture notes and you're not just working blindly in the dark. And you will be getting physical copies of the lecture notes. Since there's only 11 of you guys, I can justify, making all those photocopies and stuff.
Yes.
So when you guys get
Thank
your kids,
you.
you'll have the first set of lectures, and then you'll get the next set of lectures then when we meet for the first time.
Okay.
Okay.
Have you heard yet about Lemoore and pickups and all that? Or-
Yes.
Okay.
I will give you. Let me have a pickup schedule. 1 second. Just haven't put it in under your class yet.
Okay.
My computer has been acting really, really crazy. I may have to take it in for service again.
Mine was last week.
It's huge delays on everything.
You need more RAM.
Yeah, I guess that's what it is, huh? I'll tell my boss, I need a high impact computer. Let's see, 1.
If you like a bunch of tabs open, get more RAM.
Yes, I have everything is open because I'm working across, 3 different platforms, and
Yeah.
so it's always a challenge. Start it. Okay, so it should be under your modules tab. Find out. Under your getting started.
The kit pickup?
Yep. And I just have to change the name for you guys. Edit. Yeah, I've got in contact with all of the VPs to get permission. And I'll be putting the maps up so that you guys will know. But in Lemoore, it'll be in front of the where your counselors are located. I think it's the student service building.
Mm-hmm.
So it's Circle Drive.
By the admin office?
Yep.
Okay.
And it is struggling. Okay, so Coalinga, you can pick up the kits on Friday from 4 to 6, Saturday from 1 to 3, and Monday from 10 to noon. And Fireball, you'll be able to pick up the kit from 10 to noon, from 4 to 6, and from 1:15 to 3:30. And then in Lemoore, you guys will be able to pick up the kit at 1:30 to 3:30, 10 to noon, and 4:45 to 6 p.m. on Monday.
Okay. Dr. Henry, do we have to email you a picture of the chem kit?
Yeah, well, not email me. You're going to submit it onto Canvas. There'll be a little, it's for 5 points, 5 easy points. So just to let me know that you got your kit.
Okay. And that will just pop up on Canvas and
Yeah, there's going to be an assignment popping up on Canvas. Upload it.
okay.
And if any of you guys are far away and you need your kit mailed to you, then what you'll do is just email me, or also in that same submission, you'll be able to submit your address. And then also let me know by email. So
Dr. Henry,
Yep.
if we had a lab kit from last semester, do we still have to go to pick up like extra supplies or anything?
yes. So even if you have a kit, and that's also what I need to know, because I need to know how many kits I should be carrying with me, how many 1B kits I need to be carrying with me. Because I'm old, I forget. I know that Kayla, I know that Cassie and Taylor turned in their kits the last time. And then there's a few more people that I know that did as well. So if you let me know that you don't have your kit, then I'll be able to make sure that I have enough for everyone.
Okay.
Okay. Yeah, and we're almost there. I'm waiting for the last component to come in today. I'm hoping it comes in before noon, so then I can go and finish building the kits tonight. So.
And the registration, Dr. Henry?
Registration for what?
Well, it's saying to only students, registered, like in the class. Never
Yeah.
mind today. Okay, I was confused.
Yeah, because I don't know like your spouses, but I know you guys, and so it makes it easier. But if in those circumstances, like you can't make it and your spouse is going to make it, just have them bring your ID, and then I'll sign it off. It's also because you guys have to sign some paperwork as well to make sure that you guys are not eating the chemicals that I'm providing or selling it on the black market. Okay, so these are basically an example of, remember we talked about radio waves, right?
Mhm.
The AM radio waves. Well, AM actually deals with the modulation of amplitudes. Okay, so that's what the A stands for. AM radio is amplitude. So what is the amplitude again?
Amplitude is the half the wavelength,
Is it half the wavelength?
isn't it?
Because what is the wavelength? Draw on my screen. What would represent the wavelength for this wave? The first one up here, the signal.
It's from peak to peak.
It's from peak to peak. Okay, so from here to here. So that's the wavelength. So, oops.
Is it half of the amplitude?
Okay,
Or-
so what
Yeah,
would represent
half.
the amplitude?
Like, I guess like the height of the wavelength. Of
So
the
from peak to trough.
But
Yes.
half of that.
Okay, that's
Yeah,
right. It's half.
of that.
That's right.
That's what I was meaning.
Yeah, peak to trough. Okay, so the amplitude represents half of that distance from peak to trough. So that would be our amplitude. That's going to be our A. Okay, so AM represents modulation in that height. Okay, so if you kind of look at the waves here, you can see that it's modulating in terms of the height of it, but the wavelength is the same. It's not changing the wavelength. Okay, good so far?
Yes.
Now, FM radio is frequency. So you're modulating frequency. So if you take a look at that one right there is pretty much the same frequency. This here is a different frequency, and then this one is a different frequency. So you're modulating the frequency. And what is frequency again?
the number of wavelengths that pass through the point.
Okay. So the number of wavelengths that pass through a given point, usually based upon seconds. Good job. Come on. There we go. Sorry. Okay, so interference patterns. There's two types of interference patterns that we could end up having. One of them is a destructive interference pattern. And so a destructive interference pattern will be where you would get, let's say, one pattern going in and another pattern going in. They interfere with each other to kind of cancel each other out so you don't see anything, right? So you'll get a dark region, okay? So that will be destructive. So basically you destroy the signal that you're seeing because they interfere with each other in that way, okay? The other one is called a constructive, destructive, constructive. That one is going to give you where you have two bright regions overlapping or expanding. So then you get a little more of a brighter region than you would normally see, okay? Constructive and destructive. You guys kind of get that?
Yeah.
Okay. So here's an example. Okay, so here you can see kind of that little bit of a haze. That would be your destructive component interference. And then, let me get my little pen. So we say here. So that's destructive. Construct. Okay, and that kind of makes sense, right? It's kind of like, so if we have like one little light and it has this pattern, and we have another little light, if we put those lights together and their patterns overlap perfectly, isn't that light going to be brighter?
I would assume so, yeah.
So if you guys think about, have you guys noticed that a lot of the batteries and everything are going to LEDs? And so initially they would start off with one LED. Now they'll have 5 LEDs, and that causes that light intensity to be a lot more than what you normally see. If you just had that one LED, right?
Yeah.
Okay. Come on. Maybe. These are not wanting to work for me today. Okay. So a standing wave is basically a wave that isn't traveling. It's kind of stationary. So they're usually stationary at a point. So that's kind of like, remember when we were talking about the jump rope, right? So if you have two people at the ends of a jump rope and they're constantly just making that rope go up and down, right? That's considered like a standing wave. So you have those 2 points, those nodes at the end, those people serve as nodes, and then you're having waves that are going in between, but they're considered standing because they're no longer moving. They have a terminal point. They're stationary. Okay. So I'll show you an example here in a second. So these waves are going to be considered to be acting more of a one-dimensional way rather than, a three-dimensional way. Okay. So nodes at the end, you have this wavelength here, or this half a wavelength. So this is an example of, again, a stationary wave. It's one-dimensional. It's only going up and down in a single dimension. This is another example. This is another example. And the last one is another example. Okay. So it's defined. It has nodes, so they're not allowed to move further than that. Okay. So there are going to be integral numbers, whole numbers that are going to be associated with that. And then those whole numbers are going to represent like half of the wavelength between those two endpoints. Okay, so if we take a look, so a complete wavelength, let's say from here, that would be one complete wavelength. Okay, so half of a wavelength would represent one node. So that would be 1, that would be 2, or one integer. This guy would just be 1. So that's 1, this is 2, this is 3, this is 4. So this guy would have 4 integers associated with it. Now that's an example of quantization. So that's meaning you're breaking it down to discrete points that are associated with it, because you have that wave, in a sense, coming and breaking at a very distinct point. Do you guys get that? So that would be 1 integer. That's 1, 2. This is 1, 2, 3. This is 1, 2, 3, 4. Now, again, this is an example of quantization. It's just making discrete points. So this is 1, that's 2, that's 3, that's 4. Very discrete points that are associated with it. Very discrete breaking points. Okay. So those discrete points where they come together, those again are considered your nodes. Okay. So how many of you guys play the piano?
In my dreams.
In our dreams? Yeah, my dreams, I'm a fantastic piano player. I have an old piano that's sitting in storage that I want to get refurbished at some point, and I just need to get enough space to put it into where I live at some point too. But you know, deep in my dreams, I'd love that. Now, often when we talk about pianos, because they're harmonic and they make harmonic waves, right? They have nodes that are associated with it. Okay. So we can also have two-dimensional wave. So we can be going in a single dimension, and then we can add another dimension to it, right? So we could have 1 dimension, 2 dimension. Okay. So here's an example of 2 dimensions. So the first wave is happening in that circle pattern. The second wave, or the second dimension, which is the first dimension, is in that circular pattern. So it's just going, making that ring structure. Okay. The second wave is, or the second dimension is the nodes itself, the angular nodes. And so you have angles that are associated within that circle. Okay. So we have the radial, which are circular, and then we have the angular, which are just the angles that are coming from those circles. Okay. Yeah, no, maybe. Okay. So sunlight is a continuous spectrum, right? So it doesn't have those discrete quantization lines. They just kind of bleed into each other. So do you guys remember, do you guys have your diffraction slide?
I did.
Did? Okay.
But I
Well,
know what you're referring to.
yeah, oh, that's right. You put it back in your kit. Okay, so when you guys get it back, right, what I'd like you to do is look at sunlight. And I have an LED in my room. And so, and look at like, don't look directly into the sun, but kind of hold it up there and you'll get that little rainbow. And it'll be a nice continuous rainbow. Then do the same thing with the white light that's in your house, right? A lot of the light bulbs that you guys are currently using are LED-based light bulbs now. And so you'll see the very distinct difference. And if you can, if you're talented enough, use your cell phone to take a picture of it. That's going to be part of your lab anyway. Okay. Questions, concerns, Cash? Okay. So
Wait, Dr. Henry, before you move on. So two-dimensional standing waves will always have like angulars.
you're gonna have an angular form, and you're also gonna have a radial. So radial meaning circular like,
Okay.
okay? And then angular meaning the angle at angles. So you can see the angles that are forming here,
Mm-hmm.
okay?
Okay.
Okay. Okay, so black bodies, they're basically, they're going to be like emitters that are going to be a result of heat. So like for instance, when you guys touch light, the light bulb, how many of you guys have touched light bulbs when you, let's say you're
Yes.
going to change the light bulb as it just goes out, what happens?
It burns.
It burns because it is very hot, right? So that emission of light also provides heat as part of that temperature, okay? And that's the very unique thing about LEDs, because if you touch an LED, I mean, they're warm, but they're nowhere near as warm as that light bulb that we would normally have, okay? Okay, so that is considered to be black body, right? And really, when we're talking about black body, we're talking about radiation or energy that's going to be associated with it. Now, let's see. Here, this represents the diagram of the spectrum. So down here, this is the wavelength. This is going to be your spectrum of radiation. So how much radiation or irradiation that's being presented in that case. And so here you have UV light, here you have visible light. And so do you guys remember like the sun is providing some radiation to us, right? You guys are aware of that?
Yeah.
Okay. So if you actually look at how much radiation that is being emitted, that visible light actually is contributing quite a bit of that radiation that is being emitted compared to the infrared and the UV light. Don't get me wrong, they also contribute some, but not to the extent as that visible light. Okay. So that kind of deals with that black body paradigm. Okay. So okay. So the kind of take-home message of this is that in the black body curves, so your maximum lambda is going to shift to shorter wavelengths as your temperature increases. Okay. So, and I'll show you another graph of that here in a second. Okay. So as your temperature increase, you're going to get shorter wavelengths that are going to be associated with it. Okay. And again, I'll show you a nice little graph that'll actually depict that. Okay. So this is the increase in temperature, right? And then this is our wavelength. So your peak, you're going to get shorter wavelengths as your temperature increases. So your wavelength is going to get shorter as that increases. So you'll have a broader wavelength or a broader wave size in that case. And then here, as you get lower in temperature, it's still going to be a broader wavelength. And then here, an even broader wavelength. So wavelength versus temperature. Are you with me?
Yeah.
Okay, so hotter temperatures are going to give you higher wavelength, right? So if you, shorter wavelength. Higher temperatures are going to give you shorter wavelength. So if you have shorter wavelengths, right, what is that going to be in terms of frequency? So which is going to give you the most energy or the most is it going to be those cooler temperatures and those cooler colors, or is it going to be those higher temperatures?
Higher, probably.
Okay.
I
So-
would say cooler because it's gonna broaden. So
Okay.
you're gonna get less.
So if you guys remember, we have this equation, E equals
Oh, MC.
H
Oh, never mind.
nu, right? And then we also have, we have C equals lambda nu, right? Is that true? The C meaning the speed of light. So if our wavelength is getting smaller, what's happening to our frequency?
They're inversely, so it's increasing
Okay,
because
So it's
they're
increasing.
inversely proportional to each other.
okay. So then that means that the energy is going to be increasing, right? So here we can see at the higher temperature, we have a smaller wavelength. This represents the wavelength down here. I'm sorry, at the higher temperature, we have a smaller wavelength. At the lower temperature, we have a bigger wavelength. So smaller wavelength, higher frequency, increase in energy. And that kind of correlates with that temperature also going up, because energy is going up. Wouldn't we expect the temperature to go up? Right? So you guys remember thermal, right? You see how everything is starting to tie together?
Yeah.
Okay. I don't know why I'm struggling today. There we go. There. Okay, so we've kind of talked about Planck's, but I already talked to you about Planck's constant. So Max Planck was a physicist, and he basically came up with the derivation of, hey, this quantization of energy actually can be calculated. We can actually calculate this energy based upon frequencies that are being generated. And so he derived the equation and established what he calls Planck's constant. Okay, so here that H is Planck's constant. One, two, three, four, five, six, that represents, remember when we talked about just a second ago, those nodes, right?
Yeah.
Or that quantization of energy. So that 1, 2, 3, 4, 5, 6 represents the quantization or quantized energy level. So those are integers that are associated with the level that they're at. Okay, so he believed that atoms are kind of vibrating, kind of like those waves, but they have very fixed points and they have fixed nodes that are associating with them. By knowing which atom you're talking about, you would know exactly the node that's associated with it. And then you can use that to do your calculation for energy. Okay? And so this is Planck's constant. It'll be given to you because it's a constant. So as you can see, the word paradigm and catastrophe has come up quite a bit in this chapter. So for instance, I didn't really talk much about it, but you have the black box paradigm, right? Or a paradox. And then here we also have what we call the photoelectric effect, right? So because energy also has to do with light, and it also has to do with the fact that electrons are kind of be constantly moving, right? So electrons themselves have the ability to kind of project light or a photon or okay? And initially, they didn't really believe that, right? So they didn't believe that electrons could be ejected from a surface and then also be returning to a surface, right? And then so later on, they actually start looking at that in more details, okay? And in theory, we should be able to to calculate the kinetic energy associated with an electron being removed from like the surface of a metal, right? Because usually who wants to get rid of electrons? Which metals? Or is it metals or non-metals?
The alkaline metals?
Alkaline are very
alkaline.
excited about getting rid of electrons, right? So we should expect very volatile situations with our alkaline metals. You guys remember what you guys did in lab when you guys were looking at, I think it was lithium, sodium, and potassium?
Yep.
Yeah. If we actually had turned off the light, you'd actually see, as you dropped it into the water solution, you'd probably see a spark initially. The pieces that you guys were using were kind of small because I didn't want you guys to blow up the lab. I actually did a similar experiment with a much larger piece, and man, it was like a big explosion and everything. It was beautiful. But I managed. It was a nice, beautiful explosion. It got everywhere. So. Okay, so this is where kind of Einstein starts to come into play, right? So remember we talked about Einstein's theory of relativity is basically saying that E equals mc squared. And so he kind of brought that back to that concept that, you know, that energy associated with light is also that same kinetic energy that you're calculating, right? And so we can kind of use that aspect to sit there and help us through this process, okay? Okay, so now when those electrons are actually being released from that piece of metal, or let's say light strikes a piece of metal, right? So, and then you see those particles being released. So those particles are called photons because they're what's emitting that light. So you have photons of light that are being generated, which are just those electrons being released, okay, or collected. Okay, so we've talked about this, basically E equals HV or H nu. And here we can substitute in for nu. We can put C over lambda because we know that nu is equal to C divided by lambda. So we substitute that in there. And so we can kind of play around with the equation, right? And so then we can sit there and get, based upon the wavelength, how much energy is going to be generated. Because we know that we have that wavelength for the photons that are being ejected. Okay, so if we have a certain color light, let's say a red light, we know that red is about 650, 700 nanometers in size. So then we can actually use that to calculate how much energy that photon is actually generating by using Planck's constant and the speed of light equation. Okay. So let's say, for instance, blue light is 350, roughly. So 350 nanometers.
So depending upon the color of the light, they'll have the difference in size, but they still travel at the same speed, right? Same speed of light.
That's
Okay.
right. So the only thing that's going to be changing is the frequency, right?
Okay.
The wavelength and the frequency. So blue light. Okay, and we have Planck's constant. H equals, I can't remember off the top of my head. It's on the, oops. Okay. Good. Okay, so if we have blue light and we know that Planck's constant, can you guys calculate the energy associated? A blue light photon. So a single photon is going to give us what? So what is C?
C is your
of light.
speed of light.
Yeah, speed of light.
Speed of light, which is
2.998 times 10 to the 8th, I think.
that's right. And the units meters per second. So then it's just a simple plug and chug answer. So we'll have to change this into into meters, so that we have the correct units. So how can we change this nanometers into meters?
Conversion.
Okay. So how many nanometers will equal 1 meter?
Um, 1 nanometer is equal to 10 to the negative 9 meters.
Okay. Or we could say 10 to the 9th nanometers is equal to 1 meter. That'd be the same thing?
Yeah.
Yeah. So we get what? 3.50. Actually 3.5 times 10 to the minus 7, right? Oops. Okay, so unit-wise, seconds are going to cancel out, meters are going to cancel out, and then you're left with just joules, which is the unit for energy. So how many sig figs should I have?
Oh, shoot.
Four.
4? Are you sure?
Uh, no.
So 300, oops,
Oh, okay.
350 is how many sig figs?
3.
Is it 3?
I mean 2.
2?
It's a slow morning.
I know. Oof.
I woke up pretty late.
Yeah, me too. I was
I got-
planning to get up at 4. And I didn't get up till like 6:30. Okay, so a single photon of blue light is going to be 5.7 times 10 to the minus 19th joules.
Yeah, that's not what I got.
What was that?
I didn't get that, so I'm redoing my. Hmm. Oh, I'm a dork. Okay.
Okay, questions, concerns, Gash.
Mm-mm.
Okay. Okay, so then this kind of brings us back to that concept, because now you're talking about a particle, an electron being escaping that piece of metal or escaping the surface, right? So if there's enough energy hitting that surface at the right frequency, then we can actually get an electron to escape. And so that is going to be part of what we're looking at, the big picture, okay? So things that are typically greater in frequency are going to lead to greater kinetic energy, which allows more electrons to escape, okay? So higher frequencies allow for more escape of electrons. Okay, so now when we talk about that, if we're saying higher frequency allow for more escapes of electrons, which one are going to be higher frequencies? Gamma rays or light rays?
Gamma, right?
Gamma. Yeah, gamma is going to have a higher frequency. So does that kind of make sense? Because that also has higher energy associated with it. That's going to also cause more damage, right? Because you're having more electrons with the ability to escape to cause more issues. Even ones that you may not want to escape are going to be able to escape under those circumstances. So do you see the logic behind it and all the pieces, again, coming together?
Yeah.
You say yeah or no?
Yeah.
Yeah.
Okay. Okay, so this is just basically showing you what we just talked about. Okay, so here we have a higher wavelength, right? This is red light. Okay, red light comes in, no electrons are going to be ejected because there's not enough energy to cause that electron to be excited to escape. Okay, where a lower wavelength, this is green light, right, is able to eject some of those electrons. And then we're able to get a maximum velocity associated with it. It's going to have a smaller velocity than something that has a smaller wavelength because not as much energy is going to be exercising those electrons. The more energy that we have, the higher the frequency that we have, the more electrons that are able to go out, the faster those electrons go. Okay, so if I want something that is going to be moving electrons, causing electrons to release at a relatively slow rate, am I going to have a high wavelength item? I mean, sorry, yeah, we'll use wavelength for an example. Are we going to use a high wavelength versus a low wavelength, or what?
You're saying you want to emit and
So
then
if I
release
want-
your electrons?
If I want to release my electrons, a lot of electrons, and I want to release them very, very fast, am I going to use a high wavelength or a low wavelength?
Low.
Hi.
Okay. Now I want you to think about it, right? Think about it. I'm not saying frequency, right? So if I
Oh,
want to,
okay.
I'm saying wavelength, right? So if I want to emit more electrons at a very, very fast rate, am I going to use a high wavelength or a low wavelength?
Would you use a high wavelength?
I say low.
Okay, we'll do a poll since there's only 7 of you guys, right? So I should be able to keep track of that. We'll go high, low. Okay, can you guys see the poll?
Yeah.
Okay.
I don't know why I was thinking amplitude. It really is a slow morning.
Okay, we got everybody voting. Okay, so the end of the poll. Okay, so the correct answer would be, if I want to have a lot of fast emitting electrons, I am going to go with a low wavelength. Because a low wavelength,
Yes.
a low wavelength is going to cause a high frequency. A high
Because they're
frequency.
inversely proportional, right?
That is correct.
So the
That is
higher the
correct.
frequency, the more energy you have.
That's right, exactly. And
But
that
the
does
lower-
cause more, yes, more emission of electrons. So you're putting in a shitload of energy, you're emitting more electrons, right? Think about it. So you guys remember the flame test, right?
Mhm.
Okay.
Yep.
And so the flame test is a good example because you have to put energy in to see energy being released. So that release of those electrons causes the light to show, right? The more energy we put in, if we put in a lot more energy, we could have a lot more electrons released and we could have a lot intense light. So in other words, the hotter that fire is, the more electrons you can get released, the more, of a signal you'll see. Okay.
So basically, a low wavelength will have more emission of electron, and a high wavelength will have less emission of an electron.
That's right. Or no. Yeah. So like for instance, here, they're showing you that you have no, this is your wavelength, right? These are lambda. Wavelength is just the distance between those waves. this is a high wavelength. This is a lower wavelength, and this is the lowest wavelength. This has no electrons being emitted. This one has a few electrons being emitted at a slower speed, and this one has electrons being emitted at a higher speed. Okay, so if we want to increase the speed of electrons being emitted, we want to use a very low wavelength.
Okay.
Okay, so just kind of think about the equations and kind of like piece together those concepts. Okay, come on now. Clear. Oops. Where's my box? Let's do. That wasn't supposed to be shown yet. Okay, so when you see a light from a neon sign, we are observing the radiation from excited neon atoms. If this radiation has a wavelength of 640 nanometers, what is the energy of the photons being emitted, of the photon being emitted? So what equation are we going to be using?
That one we just used, the
Planck's equation?
HC over upside down V or
Okay.
Y.
So we're going to be using HC over lambda.
Lambda.
Lambda. So we're going to calculate the energy. Okay. So H is what?
The constant.
H is Planck's constant, which is
6.626 times 10 to the negative 34.
Units. Joules per second.
Joules, yeah.
Okay. Speed of light.
2.998 times 10 to the 8. Meters per second.
And the wavelength?
So 6.4 times 10 to the negative 7th.
Okay, meters. So then meters are going to cancel out. Seconds are going to cancel out. And we're left with just joules. And we get this beautiful answer. Okay, questions, concerns? Yeah.
Nope.
Nope. Okay. Okay. Okay, so we get, the next thing that we're going to be talking about is line spectrum. So far we've talked about continuous spectrum. So that's when the lights are feeding into each other. Line spectrum or discrete spectra are very specific lines that are associated with very specific colors. We have very defined lines. And so when we're talking about various elements, solids, liquids, gas, when we heat those up and electrons are being excited and released from those, they're going to give us a very discrete spectrum. So you guys remember when you guys looked at the bulbs, the various bulbs. So like one of them was an oxygen bulb, one of them was a mercury bulb, one was,
Yeah.
Yeah.
I can't remember exactly what they were off the top of my head, but so you guys remember that, right? And so you looked at that with the diffraction, and you had very discrete lines that are associated with that, right? So that's an example of line spectra, right? Because hydrogen has a very discrete pattern associated with the electrons that are going to be able to be emitted from there. Oxygen is going to have a different pattern. Mercury will have a different pattern from both of those. Okay.
So it's like their fingerprints then. It's
Exactly.
different from everybody else.
Yep. And we can actually use that to our advantage to sit there and identify what atoms that are in certain compounds because of that. Okay. And also because of that, we could sit there and play around. So these are neon signs. So we can actually sit there and play around with that as well and cause different colors to occur as a result of it. Okay. Okay, so those patterns also represent light being emitted at a certain energy. So they're associated with discrete energy signatures. So every electron in an atom can be excited to emit a different and discrete energy signal, okay? So this is an example. So here's sodium. And so you can see the different signature pattern, right? This is an angstrom. So this basically represents like, an angstrom is like wavelength. And so these are different wavelengths where the electrons are being emitted so that you can get that very line structure. Okay. Questions, concerns, Cash? Okay, so now what does that all mean? So Johann Balmer basically had derived an equation, and this equation is going to be kind of changed around a little bit, so we're not going to have you guys memorize this equation, but there is the inverse of lambda can be calculated based upon a constant and those integers. Remember those nodes? So because those electrons can have only a certain excitation energy level, a level that they can go up to, right? Or a whole integer to allow us to sit there and calculate it. So for instance, he came up with this equation. So for like hydrogen, he says there were 4 visible light wavelengths, right? So he says, okay, 1 to 4, 4 being the maximum that it can go up to. This is his constant that he had derived, and then the integer. So this would be where he'd actually started from. So if he started from 1, then he'd go for 1, or it could be 3, or he can go from 3 to 5, you know, so it could be excited up to a different level. Okay. So let's go back. So you see 1, 2, 3, 4. So in that visible light, that UV to, let's see, UV to red light or infrared range, right? You have find 4 discrete lines that are associated with it. So those are like 4 discrete nodes, okay? 4 integers, okay? So in the case of, let's say, sodium, how many discrete lines do you see in the case of sodium?
7.
7.
So we see 7, right? So that's 1, 2, 3, 4, 5, 6, 7. Okay, so in that case, for sodium, this value wouldn't be a 4, it would be a 7. Okay. Okay, so this is where it started from. Then Reinberg comes along, and he made some changes, right? Some slight changes. First off, he took Balmer's equation, right? Made it a little more general and said, hey, we're going to call this Reinberg's constant. He named it after himself, of course. And then he said, I'm just going to more generalize so that, you know, we can sit there and apply this concept to other atoms that are able to go to, that could give me more nodes and various integers. And also, just in case I just want to look at the integer signature from one node to the next node and not necessarily look at the integer signature from that maximum node, okay? So he said, I'm just going to leave this as N1 and N2, where N1 always has to be less than N2, where in this situation, N1 was always going to be greater than N2. So he made these improvements, and then he just kind of took over the equation, right? So again, if in this situation, if N2, and this also allows us to have a positive value where this one was always going to give us a negative one. So under these circumstances, we could sit there and plug in the different nodes that we're looking at. So if we're looking at the first node to the fourth node, then we would plug it into for our N1 and our N2. And I'll start explaining to you what these nodes are going to mean, or these integers are going to be representing here in a second. Okay, so Bohr basically took this even further. And he started really looking at, again, a physicist, and started looking more in terms of quantum mechanics. And he's kind of like the father of quantum mechanics, and he designed what we know as the Bohr hydrogen atom model. Okay, so he basically started with hydrogen, and he looked at all of the different spectrums and all the different lights and the energy signatures associated with it. He spent several years of his life doing this. And so he kind of comes up with the idea, is just, you know what? So it's kind of like that concept of planets. You guys like the sun, right? So the nucleus of the atom kind of represents like the sun. And then you have circling around it electrons, right? And those electrons that are circling around it, kind of like, let's say we have the sun in the middle. And then what is the first planet? This is bad because it shows you how use it or lose it. Is it Mercury is that first planet? Or is it Venus? Because aren't we the
He's
third?
Mercury.
Mercury.
I believe.
Okay. So
I think Venus
Mercury,
is later.
yeah. Okay, so Mercury is that first planet circling the sun, even if it isn't, we're just going to say it is for right now. So then we have Venus, right? And then we have the Earth, right? And so that first orbit represents that first place where electrons are. So Mercury represents like an electron set. And then Venus will represent another electron set. And then, you know, so you don't see Venus going all the way out where Pluto's at ever, do you?
Mm-mm.
Okay. And you don't see Mercury coming past the Earth, right? It's always staying in its orbit. So Bohr kind of said the same thing about electrons. Electrons maintain an orbit around the nucleus, right? And so he had that concept of like kind of planetary, you know, how the planets are kind of orbiting around the sun, okay? And so he kind of believed that there was an elliptical orbit associated with it, okay? Now, before Bohr, there were a lot of crazy beliefs and everything like that, but he kind of got it organized and saying that, you know, hey, to get out, for electrons to get out of that orbit, it's going to take energy to kind of knock them out, to kind of get them excited to beyond that. So you can excite an electron to go to a further orbit. So if we stick enough energy into Mercury, we can knock Mercury outside of the Earth, right? But at some point, that energy is going to have to be released and it's going to return to where it's at, okay? So he did this, and it worked great for hydrogen, but it only worked for hydrogen. Okay, so what were some of the benefits that Bohr had done to kind of get that to actually work for hydrogen? Well, he incorporated basically quantization, right? He said, you know, we have these very discrete energy points, quantized, these discrete lines that are associated with it, discrete energy levels, okay? He also incorporated some Einstein finding, which basically lights consist as photons. So they're more than just that, they're more than just a wave, they're also a particle. They have that wave particle duality. And so he also took that in consideration as well, okay? And then also that energy is proportional to frequency. Okay. And he made an assumption that normally when they're not excited, when those electrons aren't excited, they don't emit any radiation, right? So they're just, when they normally circling, they don't emit a radiation. But when electrons absorb energy and or emit energy, then that's when you get movement of those electrons. They get excited, and then that's where you're going to get radiation. Okay. Come on. So if you look at energy, the difference in energy, the change in energy is going to be equal to the absolute value of the energy, the final energy or the final orbit energy minus the initial orbit energy. And then that's going to give us a value that's going to be equal to Planck's constant times frequency. Okay, so he played with this a little bit. And then he comes up with his own expression where he says E equals a constant that's going to be a combination of the mass of electrons, the charge, and also Planck's constant. So a new constant. And then this represents those integers or those nodes that you can go up to. Okay, and so then if you actually take a look at this equation, looks very familiar. Yeah, no, maybe?
Yeah, it does.
Okay, so if we kind of take a look at this here, we rearrange our equation, we get Rydberg equation. The board just goes back to Rydberg's equation, right? And then where Rydberg's constant is just represents that K divided by HC, which are all constants, right? Oops. Okay, so this here represents that first state. This here would be the state where we're starting at, our ground state. So this represents that first integer, ground state. So at ground state, this is how much energy that's associated with ground state. Now, if we excite the electron, then we'll go to that very next state. If we excite the electron even further, we put more energy in, we can go there. If we excite the electron even further, we can go here, okay? And so, and each of those are calculatable. So this would be that first node, that would be that second node, that would be the, this will be the first node, second node, third node, fourth node, and the fifth node for that electron to be excited to. So those actually represents energy levels, right? So if we look at our periodic table, come on now, help me. Okay, see my periodic table? So they represent these values here, right? So that's the energy level. So you're saying that the electrons can actually be excited to a whole nother energy level. So that one electron that hydrogen has, if we put enough energy in, we can actually shoot it all the way up to that 7th energy level, right? Because that's the one that we know of, right? And then we can calculate how much energy it's going to take to make it go up that high, how much energy is going to be released once it's coming back down. Because how many of you guys eat sugar? A lot of sugar. Or your kids eat a lot of sugar. Come on, Selena, you eat a lot of sugar?
Yes, I have to admit.
Okay, so when you go on a binge and sometimes, I'll go through my moments and I'm all depressed. So I'll just go and buy all this candy and I'll just eat it, right? And I'll eat it. Now, by the end of the day, what's going to happen?
Sugar crash.
I'm going to have a serious sugar crash, right? So I get all high and I'm bouncing off the walls and everything like that. Then I come crashing down. That's the same thing that happens to these electrons, right? You put the energy in, right? You put in all the sugar, you shoot it all the way up, right? You shoot it up to that other energy level. And then when it comes down, it's releasing that light. That light that's being released, right? Gives us that signal. It gives us that color. It lets us know the frequency that it is. It also lets us know how much energy had been put into the system, because what we put in, it has to come out, right? Again, goes back to the law of conservation. Are you with me?
Yep.
Good. Okay, so let's go back. Okay, so ground state is where we start off at, and then we excite it to those other levels. We excite it to those nth values. Those nth values are discrete points, they're discrete nodes, and that means that we can actually calculate the energy associated with it, right? Okay, so that means that when the atom is absorbing energy, we're exciting the electrons, right? It shoots up, and then it has to come back down to ground state. Okay, there's a question. I can't hear you at all, Cassie, anymore. Okay, what is your question about K? I still can't hear you. I can read your lip. Damn it. I mean, I read your lip saying damn it, but. I'll actually give you guys Reinberg's constant so that you guys will have the value for that. And I'll also give you Planck's constant so you guys will have the value for that. Yeah, well, because K is just, like I said, it's a combination of the electron and the charge and things that are associated with it. So it would depend under the circumstance. But there is a general value that you can use so that you're not taking that in consideration. You just take in, because it's talking about a particular atom, and so it's a relative term. Okay, you understand with that? Okay. Okay, so at the end of the day, the energy that you're putting in, or the energy that is being absorbed, has to be released, and they're going to be comparable to each other. Okay. Okay, so this here basically is the model for the Bohr atom, the Bohr hydrogen atom. So this is how much energy that is being absorbed into our system, and this represents the electron, that one electron. So that electron can go to that second energy level, it can go to the third energy level, it can go to the fourth energy level, it can go to the fifth energy level, so on and so forth, right? And then when it does that, it can crash back down. In addition to it, if you also continue to put energy in, you can excite an electron from one energy level to another energy level, right? So you get it excited, you throw some more energy in there. Technically, you can excite it even further. Technically. Okay. So come on. There we go. Okay, so here, again, all my questions are coming up too soon. I mean, my answers there. So what is the energy in joules and the wavelength in meters of the line in which the spectra of hydrogen that represents the movement of electrons from Bohr orbit with n equal to 4 to the orbit with n equal to 6. So they want you to calculate the energy and the wavelength, right? So what equations are we going to use to do this? So we can start off with Balmer's equation, which says the change in energy is equal to K times 1 over N1 squared minus 1 over N2 squared. Now, N1 is going to be, is that going to be 4 or is that going to be 6?
That's going to be 4.
Okay. So N1 is going to be 4. So we're going to plug in 4 into there. They give you the value of K for the equation. Here's K. So this is going to be N1. And so N2 is going to be 6. So we just kind of plug this in. And so then we get the energy, right? So then what are we going to use after that? How are we going to calculate the wavelength? Yep. We're going to use delta E equals HC lambda. Then we solve for lambda. So we'll get lambda. Oops. Put an equal sign there. We'll get lambda equals HC over delta E. Okay. So if you plug and chug, here's your delta E. And then once we get our delta E, we plug it into the equation. We know what C is. We know Planck's constant. And then we get our lambda value. So if I want to change this into nanometers, how many nanometers is that? Anyone? Anyone? How many meters equal nanometers? 10 to the what?
10 to the -9 or 9.
10 to the 9. Yeah, nanometers. So then you'll get 1, 2, 3. So 2. So this guy is going to be beyond infrared, right? So it should be like an infrared portion. Questions, concerns, Cash? Okay.
No.
Now, good. Let's see how we're doing on time. Okay. Let's go ahead and stop here. And we'll finish this up next week. So your first lab, I'll be posting up for next week. We'll actually start doing Zoom labs officially. The first lab is going to be, it is going to be a simulation, and it'll be due next week. But I'll be posting it up tomorrow because I have to make some modifications. So because they've made some updates.
So then we don't have lab today?
There's no lab today. But if you want to do something, you can do something, you know.
I was just asking.
Okay. Yeah, so no lab today. We'll actually start, you guys will have simulations to work on, and we'll actually start doing labs next week, towards the end of next week, after you guys get your kits. Okay. Questions, concerns, Cash? Pretty simple so far, right? You guys, but you're starting to see how everything is starting to tie together. Are you guys feeling it?
Yeah.
Yeah.
Matt, you feeling it?
Yes, sir.
Okay. So I guess with that, oh, Alberto kind of creeped in the room. I didn't see you earlier, Alberto. Can pick on you.
Yeah, I've been here.
Okay, good. Okay, so then I will see you guys this weekend at some point, or this Friday, Saturday, or Monday.
Okay.
Kits. And I know one of the times I actually conflict with our lecture schedule. So I'm going to be pushing our lecture back so that I'll have time to actually give the lecture in the evening. So I'll send you guys a message about that. Okay. I'll see you guys later.
All right.
Have a good day.